Great, thanks. So we're going to talk about the sort of simpler raster-based change detection. Some of you know that in the old days we used to call this software that I'm going to show you DoD software, and that stood for DEM of difference. That was a good name until the Department of Defense and this quack. But anybody recognize? That was a nicer time, wasn't it? Yeah. So, yeah, unknown, known, yeah. It's all very uncertain. So we renamed the software because we're geomorphologists and quite interested in change detection GCD after that, to get rid of this sort of Department of Defense kind of confusion. In retrospect, we probably should have called it topographic change detection, because what we're doing with the simple raster calculation or just plain change detection really is the difference in whatever the topography is. And those differences may represent garbage due to our noise. They may represent geomorphic processes that we're interested in. They may represent anthropogenic processes. Get out my Tonka toy. I cut some earth. I fill some. I place some fill, etc. Or tectonic processes, etc. There's a whole bunch of things that could be represented in that topographic change. And what I want to walk us through today is just some of the basic principles behind this and how we get to the point where we can separate that noise and then try to make interpretations of the rest of the signal that we see there. So at its heart, this topographic change detection issue is a signal to noise problem. And what I'm going to do in the next hour here is kind of go back and forth between some slides to get the principles across, and then showing a live demo of these things. If you're really ambitious and you want to, you can go on the website and download this stuff and do it as we go, or if you already have the software. But I'm going to discourage that because I think it'll just be distracting. We won't be able to sort of keep the time. But I do want you to raise your hand or just blurt out if there's something we're covering that doesn't make sense. As I mentioned yesterday, this topographic change detection problem is easiest when it's applied to a big obvious signal, and we can, the noise is not a big deal. But for some of us, that's often not the case. And one of the things that I won't mention again this morning, but is absolutely fundamental in this, if I go back to this little guy, time. What's the time between our surveys, right? So we're going to spend all this time talking about how to look at, estimate errors in an individual surface, propagate those errors, and then use that to help us with this very simple sort of change detection problem. But a lot of your interpretations are going to be predicated on what is the gap between these things. Is it sort of on an event-based time scale, annual, decadal, something arbitrary? The noise part of this is typically estimated with some sort of error modeling, and we'll talk briefly. We won't go into much depth on any of that, and then error propagation. And when you're doing this sort of thing, apples to apples is the easiest. And we heard this in some of the talks yesterday. What I mean by that is if you've done everything in your first survey and you got that all set up and you do sort of the same things in the second survey, that's the easiest situation. It's also really rare. Most of the time, we are evolving, and improving in terms of our acquisition capabilities. We may be using different survey instruments, et cetera, et cetera. So we don't have the apples to apples luxury. Instead, you got an apple and an orange, or an apple and a pear, or whatever, and you just have to make do with it. And as long as the error modeling in that case is done independently with those, and a couple other steps, we can still play games. These terms I'll come into in a moment, but they also are relevant to, even if my methods are different, I can at least do this simple raster math. There's, I sort of made this point already. We use thresholding of our changes typically to allow the separation of the signals that we're interested in from the noise. There's more sophisticated ways of doing this with modeling. For example, instead of just modeling elevation and at two times, we can model a distribution of elevation and do subtraction, for example, on PDS of elevation. That's not done that commonly, but it's certainly possible. You can similarly, you can have PDS of air if you want. There's a bunch of games, but I'm just going to cover the sort of simpleton sort of approaches here. And really what most people do is just discard or flag as not trusting that information that falls below that threshold. What I want you to take away is that you should, whether it's raster-based change detection or anything, I would encourage you to start simple, get through your whole process of doing your change detection analysis, but do it quickly and with the easiest, dumbest methods available. And be conservative. And if you get away with it, if you can see what you're after, pat yourself on the back, sigh of relief, and move on to the interesting interpretation. If you can't, and you believe that there is better information that's sort of locked in there, then that's where you invest in more complicated, for example, air modeling methods. Okay, so I'm going to kind of go through those things, and we'll be sort of switching back and forth between the software and this. The software, you could, some of this stuff is, all this stuff is simple enough. You could do this with a whole bunch of just geoprocessing and art. You could write your own MATLAB or Python scripts to do these sorts of things. I'm going to show you how to do this using some software that we have. This is GCD7. And the website for that is just gcd.riverscapes.xyz. And there you can download, there's a standalone as well as this add-in, which I'll be demoing today. And everything that I'm going to go through at an admittedly uncivilized pace today is on there are slower paced videos that are broken out into individual tutorials, and you can work yourself through these exact same exercises. So I don't feel bad about giving you a little fire hose here. All right. So when we want to make geomorphic change detection inferences from this topographic change detection from these DODs, right? This is simply a matter of subtracting elevations of the old from the new, so that negatives show up as surface lowering and positives as surface raising. I'm going to use the convention of deposition, of raising in blue and lowering in red. Now, if I'm comfortable interpreting all that change as geomorphic, then I would call that lowering erosion and raising deposition. And so this is the basic thing that we'll do here in a moment. And the way we sort of deal with the change detection is we estimate with air modeling and air propagation typically. So I said this, right? In a perfect world, the topographic change signal that we're looking at would be much, much greater than the uncertainty in our elevation. And so landslides are a nice example, big volcanic eruptions, big, geomorphic processes. These are nice applications of this. Working in fluvial environments, we often have this sort of situation. And we are ignoring horizontal changes and the sort of the general rationale for that, and just focusing on the vertical, is that if we use cell resolutions that are larger than our sort of horizontal air, then we can sort of wipe that under the carpet. This is not necessarily appropriate for all problems, as we've already heard, and that's why most of the tutorials that you're going to be walking through are also focusing on other techniques, for example, cloud to cloud. But this air propagation problem we can look at here. If you imagine this is the elevation, this is a slice through my surface elevation at time 1. This is my elevation at time 2, and I think we can pretty safely all agree that between time 1 and time 2, the surface did what? Did it raise or lower or stay the same? It lowered, right? Time 1, time 2, so this is a slice through that. So everybody should be happy with that, but then of course, I tell you, well, this is my confidence. So this is my surface here, a very simple air model, just plus or minus spatially uniform 10 centimeters. And then I tell you that this one I did a little bit poorer job on, plus or minus 20 centimeters. And then we ask the same question, and is it a signal we can distinguish from noise? Maybe not. So the way this is typically done is just standard air propagation here. And so for the example that we're talking about, basically we would estimate our propagated air as the square root of the sum of the square of the air deflector. So this is basically, you know, it's not 30, it's a little, you know, it's 22 centimeters would be in this example what we come up with. And there's a number of references that walk through this in under much more detail. But this is sort of the standard thing that's done. Now, what you use for your air model, whether it's a really simple spatially uniform or something more complicated, that's where I mean start simple. See if you can get away with a conservative estimate. And if you need to use something that's a more sophisticated air model that would allow you to be more liberal and see more activity in certain areas, then do it. And so here are some examples of spatially variable air models, all of the same little reach of river, but surveyed with very different techniques. So total station GPS, airborne LiDAR, and ground-based LiDAR. And you can see these are the sort of estimates of the spatially variable airs across this. There's a whole bunch of techniques for doing this, and you invest in these, like I said, if you think that they are going to help you capture the signals that you're after. I will show you in a moment how to do one that's pretty simple. We tend to use a lot of fuzzy inference systems for this. They're quite flexible and easy to adapt. I would caution you from using just statistical models of air where you just sort of try to do a complete air budget and propagate all your airs into each other. You end up painting a very bleak view that you will never be able to detect anything. So a little tangent here on this apples to apples easiest part. I love that Nancy just calls it how it is. So a while ago, you know, Nancy was like asking, so what do you do? And she's like, so basically your whole career is like a simple subtraction problem, right? You know, new minus old and all this stuff. Yeah, part of it has been just that. But there are some things that we need to do in terms of getting our ducks in a row on the housekeeping to do this. So orthogonality is a pretty simple concept. So if I have two rasters here, they have obviously different extents. I have the one in black and then I have the one in red. Orthogonal rasters must share the exact same grid resolution and they share the exact same grid centers, okay? But they don't have to share the same extent for that raster. Now, this is important, obviously, because if I want to dumb this problem down, if you will, to a simple cell-by-cell subtraction problem, I better make sure those things are aligned. Right? So that's where orthogonality comes in. Now, concurrency is nothing more than a special case of orthogonality in which they also share to the same extent. Okay, so it's orthogonal, but then have the same extent. In our software, we do not enforce or require concurrency, but if you were going to go write yourself, say, some MATLAB scripts, and you were going to load in your arrays, unless you were quite careful in how you did that, the easiest thing to do in prepping your data would be to make sure that they're concurrent, so that you have the same numbers of rows and columns. You can obviously deal with that, but it just requires a little bit more effort. So then there's this concept of dimensional divisibility, and thank you to the folks at Esri for having us to even think about this obscure term that shouldn't exist. Primary properties of rasters include the cell resolution. So they include one of the corners of the of the grid, and they include the number of rows and number of columns. That's all you need. Now, Esri tries to be really helpful by providing width and height. Well, that doesn't seem so bad, right? Because, I mean, so here, look, top, left, right, bottom. So, you know, if I know what the coordinate is over here and over here, I subtract those two and I get width. Well, depending on how you do that and how many significant figures you choose to hold in memory, we get things like, well, I specified a raster that was 1.0 meters. But then you start looking under the hood, and Esri actually spit you back something that was 0.9999997 or something. And so these problems introduce little offset errors and basically mean that you're not going to be orthogonal. The way around this is just to take control when you go from point cloud to raster, or in your spec documents for acquiring data, ask for cell resolutions that evenly divide into one. So you can still go down 5 centimeters, 10 centimeters, 20, but don't do something stupid like 13 centimeters. And then round up all the raster extents to something nice, a nice even integer. And that will help you avoid having to think about this. Okay? All right. So, now, thresholding, I mentioned, this allows us to separate the signals from the noise. And so basically, to do this simple subtraction problem, I'm gonna walk you through this right now outside. We're just going to, get our two rasters in, and we're gonna do our simple subtraction, and then we're going to apply a threshold to get started here, okay? So now is the point. This is all pretty simple, but certainly if there's anything I'm doing that you have a question about, just shout. Okay? All right. So I am in a blank ArcMap document. I have this little toolbar up here, which is the change detection toolbar. Again, there's videos of everything we're going to do, so don't freak out. Just try and follow the concept. But the reason I'm going to do these sort of live demos is I want to kind of demystify it if you haven't done this, and point out that these things can be pretty straightforward. In GCD, we use projects, and so I'm just going to create a project here, and this is so that the housekeeping is kind of taken care of for you. I'll make a new folder here called demo, and we'll call this my first, GCD. So I've got this empty project, and if I were to look at what that's created on disk, it's basically dumped into this folder, this little project file that's just saying there's a project here. And what we're going to do is start adding stuff to that. So you have to load in your surveys. And so I'm going to right-click, add a survey. And I'm going to go find one. All these tutorial data sets are also on that website. So I'll steal one from the overused Scotland example of the Feshi. And so I'm going to bring in this first one. And right here, all this stuff, it's basically, see how it's showing up green? See how these raster extents are nice and rounded up to whole integers? It's basically saying this is internally consistent, the width evenly divides into, or sorry, cell resolution evenly divides into width and height. Okay, so we add this raster, it makes a copy of it from disk into our project and adds it to the map with hillshade and symbology. So that's one. We can come in, add another. So there's my 2004 versus my 2003. And of course, if one of the easy sort of just visual things for sort of raster change detection, if you have, these things with similar symbology, is just to use the effects toolbar if ARC doesn't crash on you. There we go. And so I can just sort of peel back and see some of those changes, right? But now we're going to do our simple subtraction problem in order to actually look at that quantitatively. So I'm going to come down here to analyses, and I'm going to add a change detection. And I will grab the old one, or the new one, and the old one, make sure I get those orders right. And somebody, you know, pull a random minimum level of detection number out of thin air for us. 27 centimeters? Or 25? You sure we don't want to do 27, 5, 6, 3 or something? You can do whatever here. We're going to go ahead and run that. And so the first thing what we're going to see here is it pops up this sort of little result dialog, and then we have this thresholded change here in the background. Now, the actual subtraction problem, I don't remember if I have this working right now in this version. The actual subtraction problem is not going to give us this. This is our thresholded DOD, okay? And I'm just going to go back to, where did we have that guy hiding? It was in our demo, my first GCD. And so in here, what we've done under analyses is it's created this this change detection folder. The raw is in here. And so every single cell is actually predicting change. And so if I wanted to see what that looked like, I could add a change detection here with 0. I better get the 2004 and 2003 correct. And now this is going to come back and it's going to show a change everywhere, right? And so if we look at this one, notice that the columns here, the raw and the thresholded are exactly the same. So we have a bunch of aerial stats, we have volumetric stats, and we have vertical. And so this is without thresholding, and then this is with applying a minimum level detection of 27 centimeters. So spatially, that just threw away anything that had a signal that was below that. That's all you've done there. And if we want to look at this another way, instead of just tabular results, these are elevation change distributions. And so this is no change. This is erosion or surface lowering to the left, and then surface raising to the right. And then you see this gray. This is everything that's below that 27 centimeters that's in threshold. So does that make sense to folks? Any questions on that? Pretty straightforward. Another way of sort of looking at these is, you know, you can compare the volumetric. And so notice that there's error bars on this. So this is the total volume of lowering. So about 2,000 plus or minus what? A lot. And similarly here, this is, I've got my deposition potentially, or surface raising. We can go and look at what these actually are here. And so I've got 2,000 plus or minus 1,100, and then 700 plus or minus 480. So then the difference of those is net degradational, is what we're suggesting right here, that this is erosional. We can look at that in absolute if we want to see that below 0. And that's just barely significant.
What are the errors, original errors?
Yeah, so what those come from are minimum level of detection that we've pulled out of thin air in this example, okay? So now a lot of folks will look at this and they'll get afraid. And by far in fluvial environments, probably the most common result is actually that your propagated air is greater than your calculated difference between the erosion and deposition. And so we refer to those as indeterminate budgets. It could mean that I can't detect a signal. It's also very common if your system is roughly in equilibrium. So it's not something necessarily to be alarmed of, but it is a reality of the data we tend to look at.
So,
yeah.
I'm sorry if I missed it, but when you went from the point cloud to the DPMs on the DPMs, how did you make sure that they were aligned, or that you were starting the rasterization
Yeah, it's a great question. So I didn't mention it, but in this example, we created tin, and then we went from tin to raster. And if you just let it do the default, it's going to choose extents based off the arbitrary extents of your vector tin data or your point data. And so you just round up those extents to nice whole integers so that you then have those nice orthogonal rasters.
What's your preferred platforms for grading?
It depends on the data. I mean, so it depends on whether we're talking about, total station RTK data versus, multi-beam sonar or LiDAR. I tend to like tinning and using break lines with all of it. If you got small data sets, I wouldn't do it in ARC otherwise. Yeah. Well, if it's SSM, I'm probably doing it in Agisoft. Yeah, I mean, good questions, but questions for getting to, like in Ben's diagram earlier, getting to that stage of, here's my raster DEM. And so all I'm going through right now is just assuming you've gotten there. And when we do workshops on this properly, we go through those sorts of choices. That's a great question. Okay. So back to this. We apply this thresholding spatially, and it basically has the impact on those elevation change. Oh, this is not looking so good. Can I get rid of you? There we go. Go away. So these little elevation change distributions down here at the bottom, when I apply some threshold, I basically am just swiping the middle right out. Okay. All right. And so what I would encourage you to do is see how far you can get with some sort of defensible, and I'm deliberately not defining defensible, but there are lots of documentation to help you with that choice. Minimum level detection, see if that'll work for you. That might make sense in sort of an apples and apples thing. What I'm going to do is walk you through how we progress on making this more complicated. And I'm going to start with our choices for thresholding, and then we'll come back to air model. Question? Yeah.
Are doing your blanking centered around 0? Is there ever a circumstance where there's some sort of bias where you wouldn't want to have it centered around 0?
Like what?
I think I would say
Yeah, the erosion magnitudes are often higher in a fluvial setting. Yeah. You definitely don't want to start down this road until you've dealt with datum issues, which, now that all these repeat LiDAR data sets are coming online, even if they appear to be the same datum and projection, doesn't necessarily mean they were surveyed with the same ground control. So there's a whole bunch of issues on the pre-processing to get up to this. To your question, is there ever a case? I mean, we do know that in a lot of situations we have this negative bias problem where when we just apply that uniform threshold around 0, we're ignoring that bias where a lot of the depositional signal in a fluvial environment is low magnitude and then falls underneath that. That is one argument for some more sophisticated air modeling, that if that low magnitude stuff is also in flatter, smoother areas, they also have lower air associated with the elevations there. The real way to deal with that would be to model PDFs of elevation and do your different thing on the PDF, but more work. So we'll stick with the simpleton stuff and see how far we get. So we just did this simple defined minimum level detection, but someone just pulled out of their ass 27 centimeters, right? Where did that come from? So I mean, we didn't even talk about what kind of survey this was, right? We just said, yeah, 27 centimeters sounds good. We all went with it, right? I'm happy. So if you want to, you could do, you know, even if you don't know what's an appropriate thing, you could just do a quick sensitivity analysis. And you could see, well, how does varying that threshold change the result, right? And so here we go with that, you know, obviously our unthresholded. Here's 5 centimeters, 10, 20, 50. And you can see the sort of subsequent information loss. And you might convince yourself at some point, it seems like I'm going from what might look sort of noisy and pixelated. I'm not real sure if that's something I trust, to something that maybe is a little more coherent. I don't know, maybe somewhere between. And so this is just a matter of repeating that same exercise. So one of the things that we try to do in GCD is encourage you to explore playing with lots of different options for the same calculation. So what I'm going to do here is a batch change detection instead of, I mean, you all saw before we did 2 change detections. We could do that again and just, you know, repeat. But if I want to reproduce what we just did, I can just go to batch and I'll do multiple uncertainty analysis here. I make sure I get my 2004, 2003 correct. Okay, so this is the new and the old DEM. And then what I'm going to do is I'm going to add multiple minimum levels of detection. And let's say I start at 5 centimeters and I'm going to go up to, I don't know, 50. And let's do that at a 5 centimeter interval. Okay, and I hit add to batch, and it just basically builds a queue of things we can run, right? And so then we hit run and wait a few seconds, and then this will just clutter up our project with a whole bunch of these different things. Okay, so what this is, it's the same DOD, but just with we're using several different. I guess we don't need to listen to seagulls. I can turn you off. Oh, I shouldn't do that. Then recording won't work. Never mind. So here it's added all of these in, right? And we can, you know, go down to this. One way of visualizing these quickly is I could go into, here's the 5 centimeter one, and you can see that it's a much smaller threshold taken out of the middle versus I can go up to this 50 centimeter one, right? And we've taken a lot more out of that. Okay, so that's pretty quick and simple. If you want to, another way to sort of visualize these, if I add all those to the map. Good way to make ARC freak out. But if I start, let's see, the best way to do this is, someone probably knows the easier way. So there's my 50, right? There's my 45, 40, right? You can see that we're recovering information, obviously, with that threshold. We keep going, and you know, you can eventually get all the way down. Oops, that one, to this one, okay? And so, but a quick way to sort of say, look at that is that sensitivity analysis is you could just do a little inner comparison. And so I could select all of these, get rid of that 28 one, and I'll just call this my little sensitivity analysis to min-log. And what this is going to do is give us a little Excel file. It's actually, here's an XML, but it really is an Excel file. So let me just find Excel. All right, so if I just drag you in here. There we go. So this is those aerial stats, so surface area of lowering and raising for the raw and the thresholded. These are the volumetric ones right below it. And so each row here is each one of those change detections. And so we can sort of see how the values change, you know, and if we want to kind of summarize that, here the average total thickness of difference, right, is varying across these things in the 50 centimeter threshold. It's estimating it at 1 centimeter plus or minus 1, right? All the way on up to the 5, where it's estimating at 6 plus or minus 2. So you could plot that and you see what the sensitivity to that simple choice here of that minimum level detection. Does that make sense?
So bad scientists then would use this to say, well, I think my uncertainty was here, where I had plenty of good results, right? Well, scientists then would use this to look at this and say, next time I survey this, if I'm wanting to be able to detect change, I need to modify my technique to bring my errors below this threshold.
Well, we haven't even touched air modeling, right? Right now. And one of the misconceptions sometimes is if I do air modeling, and particularly sophisticated air modeling, that I can make my surfaces better. I can't. You have to do what you're saying and do a better job surveying in the first place. But if you're in that situation where you believe there's something there, then we can go there. But this is still a reasonable thing to do to explore what's going on. Now, another very simple method. We come back here, is to do propagated errors. And for this, we're going to need an error model, okay? And what we're going to do is we're going to still specify the two surveys, but then we're going to associate an error surface with it. And we're going to do this basic exercise here that we talked about. So we'll call, we'll put in a couple of values for error models here, and then we'll propagate those errors through. So let's just do that. And to do that, I need to come up here. Oh, that's nice. And I'm going to calculate a new error surface, okay? And I'm going to just do about the simplest thing I could do. So these are RTK GPS surveys. So an informed guess. And, I mean, I liked the 27 whatever, but informed guess. Huh? No trees. Nice braided river. What? 3? Okay. You guys are pretty optimistic, but fine. RTK optimism. All right. So this just created the world's most boring, if I turn off these analyses and I come to 2003, the world's most boring air surface. It's 3 centimeters everywhere, okay? But I've got that in there, and I can do another one, calculate a new air surface. Will be a little more realistic this time. RTK realism. Okay. Whoops. What happened here? And just like running lots of change detections, I can have as many air surfaces as I want. Just keep stacking them in here. Maybe I could load up some that's maybe derived from my point cloud off of a roughness model, whatever you want to do. And then I could compare what these different things would look like. So now when I come in to do my change detection, I still going to do 2004 and 3. I'm going to switch to propagated, and notice when I switch that now I have to choose from that list what air model I want to use. And so I calculate this, and this is basically the equivalent of 1 standard deviation when you're propagating the errors in this fashion. And so this is your sort of confidence at 1 sigma, if you will. And so I have way too much stuff. Oh, this is another sort of cool thing. I'm lazy, or let's say the inconceivable happens and I lose my map document. It corrupts, right? I just got rid of everything. Well, we're just fine. I'm just gonna add all those DM surveys back to the map. And now I only want to get my propagated guy in here, so I'm going to add the thresholded one to the map, and there we go. So this is what we just did, and in terms of the result, this is going to basically, if we use an input of, what did we use again for our air values? We use 3 and 5. So 3 squared is 9, plus 5 squared is 25. 9 plus 25 is 34. Square root of that is. So this is about, 6 to 7 centimeter minimum level detection is basically how that threshold got implemented. But in this case, it came from having two independent air models, and they could be different. So this is what I meant when I said apples and oranges, apples and pears, or whatever. It's you, as long as you do your air modeling independently, and you have some objective basis for that. I don't care that my survey methods are improving over time. I just need to reflect that in my air model. Okay? Questions? Does that make sense? These same principles apply to any change detection problem. This is not just unique to this. All right. So it turns out there's another thing we can do that can be a helpful way of communicating this. Let's see. No, this is just kind of fun to scare you. I don't know if you believe these numbers, but these might be some rules of thumb for a few common survey methods. You just kind of do the math on the air propagation, and then this kind of translates those to the sort of minimum levels of detection we might be talking about in those technologies. If both of them were the same method, exactly. Yeah, good point. But we can also look at this question probabilistically, and instead of thresholding based off of a specified minimum level of detection, or in the case of propagated, a calculated, we could say, let's use a probability confidence interval, and so only show me the changes that I have a 90% probability or greater chance of being real. And the way this is done is basically using some simple inferential statistics, and we basically use a student t-test, and what we're doing is comparing the magnitude of the change, the DOD, basically, in every single cell to the air model. And then if we assume that this, two-tailed test and t is significant, t equals 1 would be 68%, which is basically what we just did. Et cetera, we can basically come up with these probabilities. And so what I want to do is just show you how to do that real quick. And we add a change detection. We do it probabilistically. We choose the air surfaces again, just like we did with propagated, but here we specify what probability we'd like to do. So if you wanted to be more conservative, you would choose something higher. And if you wanted to report a little more liberally, you'd use something lower. 80% is a pretty good rule of thumb for which there's a lot of literature that sort of justifies that choice. And so I need to turn off now propagated, but here I have this 80%. So all we've done is vary air models. Is vary the thresholding method here, and we've used some really, really simple air models, but it's quick, it's easy to do these things. Yeah. It's based off of a student's t-test. Yeah. So, and you could and should, and you could argue the merits of that, but it is a convenient way to communicate your results if you want to say that I've thresholded out anything with a probability less than X.
How does that look on your histogram?
It's the same. The histograms are not going to look any different until we start putting in a more sophisticated air model, a spatially variable air model. Okay?
It's still coming up with just singular value.
Yeah. So you're going to get a little bit of, instead of just, notice how there's, the middle isn't entirely cut out. There's a little bit of detail in here. Let's do this. That has to do with the fact that you're calculating that probability and it's spatially variable. It's not the same probability everywhere. You're actually calculating the probability in every cell, and then you're throwing out the ones that are below the threshold that you use. Okay. So what I want to do lastly is just show you a couple of other approaches. I'm not going to actually demo this, and then show you a couple of features that you might find useful in the GCD software. So the fuzzy models use simple inference systems or rule tables to compare things that you can model spatially So here's slope and point density, and then what that would result in terms of the output elevation uncertainty. The whole magic in here is using fuzzy membership functions and calibrating that to what are independently derived reasonable ranges of error values. But what you can do is take spatially variable inputs that must contribute to uncertainty, and then you can produce these reasonable spatially variable error models, which in this case are pretty much just showing that the steep areas that have lower point density are going to have higher uncertainty, and the flat areas with higher point density are going to have really low. Okay. So I think that's all I want to say about that one for now. And I do want to mention that if you're working with point clouds, there's a number of tools for sort of dumbing your point clouds down to smaller data sets, decimating these down to smaller data sets that you can then build simple raster models from. TopCat is one of those options. That used to be built into GCD. It's actually in its own little toolbar now. So this is a common method. And so here is an example of basically a detrended standard deviation roughness model. And you could actually use those roughness models. This is off of some PLS data to act as your error model. That's a good approach to use. Dan Buscom's also got some great software, Pysesa, for playing some of these games, and instead of having to choose a grid resolution at which you do the analysis, it's basically doing it over a multi-scalar sort of window. So in terms of a couple of other features that are sort of new and handy in the GCD now, I'm going to actually open up a totally different project here. And one of the advantages of having everything project-based is you can ship these projects around and people can use them in, everything that you just did, you could just zip that up, you send it to someone, and they could open it up. I could take this project that we were just playing with. This is actually what I just opened here, is a standalone version of the software. Does everything we just did, but with no mapping. So if you want the mapping, we're lazy. We don't want to do all that. So we just haven't had the development budget to put maps in here. But if you want to open up the project we were just working on, let's see, that's in the demo, my first GCD. I open it up, and here I've got that whole project, and I can go and do everything that we did before. I just don't have the map visualization. One of the advantages of this is obviously I don't need an Esri license. Another advantage of this is it's 64-bit. ArcGIS is 32-bit, so that basically means you can use all the RAM on your machine. So a lot of times we'll do a bunch of our analyses in here and then just open the project up in Arc for visualizing it spatially. Okay, so I'm going to close this project. And I'm going to open up another project that I made, and just so we sort of put this to the test a little bit better. So this is a river on the North Island of New Zealand, and this is from a repeat LiDAR survey. So here's one from 2003. And here we're looking at a little bit more respectable length of river. So there's our distance tool. So what have we got here? This is about 30 kilometers of LiDAR here. And what some of the other features that I wanted to show you is now we have a reference surface library, a mask library right here, a profile route library. And basically, what the reference surfaces allow you to do are, in this case, they have set reference surfaces for gravel mining, and they basically have these elevations that they've determined that if you're above here, we can do gravel mining, and in fact we want to, because even though they're braided rivers, they are all levied, and so they need to maintain flood conveyance capacity. And so you can do your differencing instead of just between the DEM. You can come down and you can do a difference between that and, say, your current survey and your grade level surface that they have here. And then you could identify places where you're below, and we need to allow some more accumulation of gravel, for example, versus places where they might want to do this. Now, this is a little bit bigger data set, so this is going to take a few seconds, but that's a pretty powerful sort of way to, you can load in any of your own reference surfaces. If this ever finishes, what you can also do is derive reference surfaces that are, the min of a whole stack of your DEM, or the max of a whole stack of your DEM. And if you specify the air model with those, it'll go through and grab and build a composite air model based off of all of your things. And so comparing, for example, to your min elevation ever experienced to your current is basically your current sort of storage, temporary storage. Looking at those, if you look at max minus min, you might convince yourself that's sort of a transient storage analysis.
Not a good way to make it detrended.
You would want to do something else. You could load a detrended surface, and but as a reference surface, but you wouldn't want to use those as your detrended surface. So in this case, I will need to zoom in order for this to make much sense. But this is basically showing, areas that are above the light blue and below that reference grade surface. You can also add in masks, and so you can add in an area of interest, so you can clip all of your analyses down to a common area. You can add in a regular mask and a directional mask, and I actually have a directional mask here already loaded. And in this case, that directional mask is basically broken this whole area. Oops. What did I do? I wanted to get rid of you. So you can see these lines. It's probably easier if I just turn off the survey here and zoom to the whole thing. But I've got this broken out into these streamwise reaches, and I can come down and I can use that. And I can do a budget segregation where I use that shape, and it's basically going to summarize all my results, give me all my stats in each of those. And there's also a morphological approach tool in here now, which I won't demo, but which allows you to estimate sediment fluxes if you want to go there, if you want to trust that sort of approach. So this is, a little silly of me to use such a big data set to do a live demo on, but I'm kind of doing that deliberately to show that even in ArcGIS and over some respectable distances, you can still do a fair bit with some of these. There's profile routes as well, and those profiles you can enter in long profiles or cross sections, and then you can put those into a cross section explorer that is a separate piece of software, but it's also free. And that'll allow you to visualize cuts and the errors and all of these things in that more traditional sort of 1D view. It's also a great way if you have a legacy, and in this case they have over 30 years of legacy cross-section data. And so if you want to turn this data into the same currency as that, it's a very quick and easy way to do it. And then that whole cross-section explorer tool gives you a bunch of ways to do that. And if you're looking to find that, if you found this tool, basically under the help, there's a cross-section viewer website, and that'll take you there, and you can download that. So that's about all I wanted to cover to keep us on time. If there's a couple questions, I'm happy to answer it, but it's more just to reiterate those really basic sort of principles of change detection, and then illustrate one way in which you can implement some of those if you happen to be doing raster-based change detection. And also, it was a great way to encourage your post-lunch food coma. All right. Questions? You've talked too much, Ben. In a minute. Yeah. A virtual machine always works well. I don't know. I'll have to ask North Arrow, our developers. There was of an older version, but of this one, I can't remember if they've actually coded up the GUI in a platform independent way. There is a web app version of these things, and we also have all of the underlying, well, everything's open source, but all the underlying code is also available for on AWS with EC2. Some of the stuff you can put in Lambda too, and so you can batch a lot of. Ben, haven't gone there yet, but we will. Yep. Okay. Cool. Yeah. Mm-hmm. If you have two surveys that are both point clouds, yeah, I mean, and all raw topographic data it is, originally a point cloud, regardless of how dense it is. Yeah, you would want to construct your surfaces and your favorite sort of method, get those into some orthogonal surveys. Don't have to worry in this case about trying to clip those down to common extents. You just put them in at whatever they are, and then it's going to let you do the calculations wherever the intersection is, or you can impose your own area of interest after the fact. I wouldn't, though, say that you necessarily, that's what you have to do. It's just, if your questions are such that raster-based change detection is good enough, this facilitates doing some of the, the standard things that people tend to do, sort of set standards for how we keep track of that information. Yeah.
Oh, you give examples from that. What happens if you have two surveys and one happens based on the change, and then have survey difference, and which differences are not errors, but real differences due to the surveying, and then you wouldn't want to propagate those changes as an error correction to your, or not that, they're local places where the surveys result in differences that.
Yeah. So, I mean, you do the best you can with your air modeling, and if you did a great job with your air modeling, hopefully it reflects and captures that. But if it does not, what we'll tend to use afterwards is either building areas of interest that reflect that, or using what we call masking and budget segregation to exclude the areas that you tried to do your best, but you're looking at it and it's still garbage. And so one very easy thing is this multi-method air modeling is to enter in a polygon mask at the air modeling phase. And if you've got something that's really an area that is garbage like you're describing, you just produce a spatially uniform air for that particular part of the survey that's really jacked up. And so that it won't ever, so that it's higher than any of the elevation changes ever will be, so that you're forcing it to not be included in the survey. I mean, there's a whole bunch of ways you can do it. Yeah, it's rare that your air models are going to be, when you're just running them in an automated fashion, that they're going to get it all right. You still need to look at it. Okay. All right.